before I talk about Wasserstein discriminant analysis, its root is from linear discriminant analysis. So let's just review linear discriminant analysis. Linear discriminant analysis. So the goal of PCA is to maximize variability. For example, PC, you want to find these principal components x1 and x2 such that to reduce the dimension, but you are maximizing variability, maximizing variation. But the goal of LDA, or linear discriminant analysis, is different. You want to maximize separation. You want to maximize separation of different classes, between classes, and on the other hand, minimize within class. So you have two different optimization in one problem, which is LDA. Also, I want to compare SVM and LDA. In SVM, you can say it is a discriminative. Discriminative, it means, for example, it is okay to know the conditional distribution. You don't need to know the problem very perfectly, but the goal in LDA is generative. It's a kind of generative machine learning. You want to know everything. Another way that we can differentiate LDA and SVM is that LDA focuses on points but wants to minimize the overlap of distributions while maximizing separation of means. So you want to maximize separation of means, and simultaneously, as I said here, you want to minimize within class variation, minimize overlap of distributions. While maximizing for example, here you have some points in one class and some other points. Okay, so the mean of this class is here, and the mean of this class is here. You want this mean to be as big as possible. This is LDA, and this is the low dimensional. For example, for two classes is 1D curve, 1D line, and so you see that you want to maximize the difference between the mean of class A and class B, and also you want to reduce within class variation. So you don't want to vary this very much. You want to just reduce the variance in the new space that I will talk about. And but SVM, you want to find in SVM is different from LDA. The goal is to find for example, these points that are difficult to separate. This is from class A, and this is from class B. This is from class B. These points that supports the margin, this one, for example, supports the margin. These are hard to classify. So all of the attention of SVM goes there. But in LDA, if you just have, for example, one scatter, then the other class, for example, class B, and this is class A, the mean of this is here, the mean of this is here. You want to find you want this distance to be as big as possible. This is the goal of LDA. You don't care about those points which are on the margin. And so you can say it's a kind of global approach. Not care about some difficult points. For example, you don't care. It could have some overlap as well, but the mean of them is maximized as much as possible. So you see that I have PCA, the goal is separation between, you want to maximize variability. In LDA, you want to maximize separation between classes and minimize within class variation. And SVM, you want to find some hyperplane that also take care of the points that are very, very hard to classify or distinguish. So let's talk about Fisher discriminant analysis. It's just another name for LDA, which is linear discriminant analysis. Fisher discriminant analysis. The idea of Fisher, the great statistician, was that we want to, so the idea is that we want to reduce dimensionality, just like PCA, but here with a different objective. So we want to reduce dimensionality to one dimension. For two class, it's just one dimension is enough. So Z is W transpose X, X is D by 1, and W is Y, W transpose is 1 by D. So overall is 1 by 1, so it's just a scalar, which is sum of WIXI, I from 1 to D features. You have D features. And so the goal is to find a direction such that projected data, this is projected data, are well separated. Okay, so you have, for example, you have class 0, which is the mean of these points. That's yi is 0, labeled 0. Also, you have another class 1, which is you can find the mean of them like this. Yi is 1, xi, but here yi is 1, labeled 1, but here is labeled 0. So now we want to maximize the goal 1 in Fisher discriminant analysis. Maximize the distance between projected class means. And the goal 2 is to minimize within class. Between class, within class. Maximize between class, minimize within class. So you want, when you want to transform to another points, so our design is just W. So we want to go D by 1. We want to find a one dimension. This is one dimensional. Okay. So after transformation, I don't say it's just a projection because it's just Z is just one dimensional. Mu1 becomes what? It becomes W transpose mu1. The mean in transformation, it is easily seen that it is just this. And for mu0 class, the same for mu0 class. And so also, not only mean of them is transformed like this, Also, the points are projected like this. And also, we know that the covariance of class 1, the covariance becomes quadratically changes. So in this space is this. For example, in portfolio management, this is the variance. Automatically, it is like automatic projection that we always do. Okay, so your covariance also goes like that. And also for covariance for zero class as well. So, you have everything to do your optimization. That I said we want to maximize separation. Okay, let's maximize. Let's maximize the distance. Maximize the distance of projected means. So I want to maximize omega W transpose mu 1 minus omega transpose mu 0 transpose omega transpose mu 1 minus omega transpose mu 0. So this is just the Euclidean distance between omega transpose mu 1 and omega transpose mu 0. One can say, okay, why just Euclidean distance? I can do Mahalanobis distance as well. So that is metric learning and those things. And so you see, all of them are related to each other. And in trace, if you just expand this, that trace of a scalar, you can just, for example, so here it becomes mu 1 minus mu 0 transpose W transpose mu 1 minus mu 0. So, in transpose, in trace, we can just rotate elements. And this one goes here, and then after that. So after rotating them, you have W transpose mu 1 minus mu 0, mu 1 minus mu 0 transpose W. So this is D by D matrix, and we say SB. This is between, B is between. B is between. You want to maximize between between classes, separation between classes. So SB, you call it. So it's a rank 1. So it is between class. We call it between class covariance. So it's a between class covariance. And it is rank 1 because you are just multiplying two vectors. This is one vector, this is another vector, so it is rank 1. And you see why this is important. This is rank 1. And why it is bad that this is rank 1. And so also the other goal is to minimize within variance. Minimize variance of each class. So we want to minimize variance of class 1, which is this one, plus variance of class 0, which is this one. So you can summarize it like this. Sigma 1 plus sigma 0, these are the covariances. And so we define this as SW. W stands for within class variance. So the goal is beautiful because the goal is to first simultaneously, so it's a multi-objective optimization. It's not just a scalar optimization. Of course, many people use scalar optimization because it's easy. And also you want to minimize within class. SW within class variation. So you want to maximize between class variation, so separation of classes. But here you want to minimize within class variation. So in other words, you want to maximize SPW divided by omega transpose SW double. This is the quotient-Rayleigh approach. And so how do you want to solve this? One way to solve that is just maximize the denominator, which is W transpose SPW, subject to your denominator, which is W transpose SWW is equal to 1 in circle and or a sphere. So your Lagrangian is so easy. You just write the omega transpose SPW, and your Lagrangian multiplier is lambda because it's an inequality. You don't care about it. It could be negative, positive, and then multiply by S transpose SWW minus 1, and you always set this equal to 0. So let's do it. You differentiate with respect to W. This means, because it is quadratic, it is simply 2 SPW minus. Differentiate this with respect to W, it becomes 2 lambda SWW, and set to 0. You will notice that SPW is equal to lambda SWW, and if you just assume that SW is not singular, so let's assume that this is not singular so that we can inverse it. So SW minus 1 SPW is equal to lambda W. So this is very easy because it's just eigenvalue. It's finding eigenvalue and eigenvector problem. So W is the eigenvector of this problem. So it's a generalized eigenvalue. This is the generalized eigenvalue problem. So if you inverse this, and this is the eigenvalue problem, and SP is rank 1. I said it is rank 1 because it's multiplication of two vectors, and SW is full rank. So the multiplication of a rank 1 and a full rank is just rank 1. So it is rank 1. So you only have, unfortunately, you can only have one direction. But in PCA, you had many directions. And I will show you that for K classes, you can have K minus 1 eigenvectors or K minus 1 directions. I will show you. And so let's do it for K classes, because now this is just transformation. W is no longer a vector. This is a matrix. So it's a generalization, because W is something like this. W this vector and W K minus 1. We want to find K minus 1 directions. So W is now a matrix. Let's do it again. You want to minimize variations between classes. Plus, this is for class 1. This is for class 2. And This is for class K minus 1.